In previous classes, it was said several times that the deterministic and stochastic methods for assessing risk had the same principle, but the methods were very different. We are now going to briefly present the methods and concepts behind the stochastic assessment of risk. The first and the most relevant difference is that in a deterministic model, the parameters are defined as fixed values, while in a stochastic model, they are defined as probability distributions. So what is a probability distribution? It's a mathematical function that provides the probabilities of occurrence of different possible outcomes in an experiment. They are also called frequency distribution. Let's see some examples to illustrate it. In a deterministic model, the value of the parameter is fixed. So if we had to represent the prevalence of a given disease, we would say, for instance, 20%, because it's the most likely value. But if we measure the prevalence in a population several times, it would be almost impossible to always obtain the same result. So certainly variability would play its role. In order to include the variability with a great amount of uncertainty, we could say that prevalence is somewhere between 10 to 30%. In such a case, a graph of probability distribution would be like this. And here we observe that any value of prevalence within the defined range has the same probability of occurrence. Even more, in 95% of cases, the prevalence is comprised between 0.105 and 0.295. In some cases, we may have more data and therefore be more precise or less uncertain. So here we have three values, but still we say that prevalence is comprised between 10 and 30%. But we add another data point, and that is 20% is a more likely value. So this allows us to produce this type of probability distribution, where 100% of possible results are included between 10 and 30%. But not all of them have the same probability. And 20% is the most probable outcome. Now imagine that we are in the best case scenario in which the prevalence was estimated by sampling. So in this case, to better illustrate the example, let's say that we have two samplings, one with sample size 100, the other with 500. Both obtain the same prevalence, that is 20%. So the first sampling is represented here by the blue line. Note that the most frequent result, if we represented this sampling many times, would be 20%. The red line represents the other sampling, where the possible results are also distributed around 20%, but they are less dispersed. This highlights the effect that uncertainty has on the ability to predict. So the larger the sample size, the smaller our uncertainty, and the better our ability to predict. And this is valid for any other type of variable. So the more we know, the better we can predict. So there are many types of probability distributions, in fact more than 80. But the good news is that in our field of interest, there is only more like 15. The key point of stochastic risk assessment is the definition of parameters by probability distributions. But this exceeds the scope of this course. So the other important point is to understand how the procedure uses distributions instead of unique values. So in deterministic models, we have the values of the parameter, and we calculate the probability value by doing the necessary mathematical operations. So you already know that anyway. So in stochastic models, things are different because we have distributions. It's not possible to do mathematical operations with distributions. The way to solve this limitation is to do it in an iterative process, something that can only be done using informatics. And the result of the process will be a new distribution. Let's see this in more detail. We have the parameters defined as distributions. So when the model is run, the first iteration starts. A random number for the first parameter is drawn, but it's not any random number. It is the one that follows the defined distribution. The same will then be done for the other parameters. Now each parameter has a single value. And the operation can be performed and the result will be kept in the RAM memory. The same process is repeated for the second iteration, and that should produce a different result. And this will be repeated for all the defined iterations. There may be several thousand of them, represented by n. At the end, there will be thousands of results in the RAM memory of the computer that will be presented in a new probability distribution chart.